Oh, I mistakenly clicked the wrong button to stop the recording. I'm sorry about that. So directly restart it again. So uh, I oh yeah, I am going to do the tree method from 10,000. So start from 10,000 baby samples. All right. Then 1% is the probability of defects. So 100 baby, 1% of 10,000 is 100. So 10,000 babies do have birth defects. And then the other 9,900 babies do not have any birth defects. Okay? Then you again, so think about you got 10,000 files, charts about medical charts about babies, and 100 is on this pile and the other 9,900 on the other side. And among 100 babies, 99 babies will correctly get positive result because that is the detection rate. If you have defect, positive result will be 99%. So that is 99 babies. Okay? But one of them, the other 1%, will get false negative. Even if you have defect, 1 out of 100 can get a negative result, which is an error, right? So 1 will go the other pile, right? So we started from here now because the condition is defect, having a defect. Now change the condition. Now, among those who don't have birth defects, 9,900, 90% will correctly get a negative result, right? That 90% of 9,900 will be is this much, 8,910. They are true negative results. But this means 10% will get a positive result even if they don't have any defects. So 10% of them is 9,900, 990, right? So they are false positive. So we'll get true positive, false negative, false positive, true negative. So already we classified 10,000 observations into 4 different categories. This is all we want. Using those numbers, you can put those numbers in those 4 unknowns. Then we are good to go. We have this frequency table. From here, it is easy to calculate this conditional probability. Given positive result, what is the probability of defect? Try this. It's easy. So let me show you the answer. So the condition is P, so you only use the first row, right? Out of these numbers, we see only 99 defective rate. That is, so out of this much, 99 are really defective. That is 9.1%, right? So actually again, back to our situation. I was told that my kid is at a high risk, and my doctor told me that detection rate is 99%. It's super accurate. Oh no. But actually, the real probability is nothing to do with 99%. It's 9%. And actual numbers, actual medically correct numbers this is much less than 1%, right? So birth defects do not happen that often. So this is much lower. So, and this is also pretty, I don't know. And in the end, the actual probability is much lower than this. Fortunately, I understand this idea. I understand conditional probability, and my wife also majored in statistics, so she understands this. So we did not panic, but I guess a lot of couples would be panicked if they hear these results. So someone has to explain that, I thought. Someone has to explain this before they get the screening test. So I hope this helps in your life. if you are in a similar situation, remember this chapter and watch this again. Of course, without the tree diagram method, you may apply Bayes rule directly. So Bayes rule goes like this. So plug in detection rate and selectivity. What is the net? Specificity rate and probability of defect. So then you get something, recalculate that, you will get the same result. Okay, thank you for watching. This is the end of chapter 2. In chapter 3, we are going to start a new topic, uh, namely average, about average. Okay, thank you for watching and I will see you then.